Hey, this is Mr. K, and today we're going to go over the first part of the Fundamental Theorem of Calculus. So I have here an integral with one variable, and then within the integral I have a variable of a different variable. And so essentially what this first part is saying is that if I have an integral or an antiderivative, and then I take the derivative of that, they're essentially going to cancel each other out. And so I'll show you the long way, and then I'll show you the shortcut. So first, the long way would be if I were to integrate the cosine of t dt from 1 to x, what that would look like is the integral of cosine would be sine. So this would be like sine of, now I'm going to use my upper limit, x minus the sine of my lower limit, which is 1. But I want to differentiate or find the derivative of that. So this is this is me doing the integral and upper lower limits. But now when I want to go to take the derivative of that, I know that sine 1 is just a number, and the derivative of any number is going to be 0. And then the derivative of sine is cosine. So this will just be cosine x, and so that would equal just cosine x. And so you can see here, I essentially just replace the t with the x, which is what's going on here. So for example, if I wanted to find dx of, we'll take another integral, we'll say from 0 to x of 1 over 1 plus x, or we'll say t squared. We could use a different variable. T squared dt. That's just going to be equal to 1 over 1 plus x squared. That's it, done. Because when you integrate and then differentiate, those again are kind of canceling each other out. The 0 here would just go away because that's just going to be a number, and so you're left with just, and that'll go away once you do the derivative. So that's why you're just left with the upper limit part, which is just be substituting in an x in there. It can get a little more complicated. I'll give you 2 more examples of that. The first one would be if we had dx. Now let's say I had the x on as my lower limit, and then again, this part doesn't matter. We'll say the square root of t minus 5 dt. Okay? So again, here though, because the x is in the lower limit, what you can do is we can use our integral rules, and we can say that's going to be equivalent to, if I were to do dx x of negative, and then now I can switch my upper and lower limit, so it'll be 3 to x of the square root of t minus 5 dt. And now we can just do it like we normally would, only now I'm going to have this negative that's going to be coming along for the ride as well. And so this would be equal to then negative square root of x minus 5. And that's it, done. One final example is what if it's not x? What if it's something different like x squared? So if I were to do dx, I'll show you the long way and then the shortcut. We'll say I'll go from 0 to x squared of, we'll go back to that cosine t dt. So again, when I integrate, I'm going to have sine, only now I'm going to have x squared, replacing my t, and then minus sine 0, and I'm still going to be differentiating that. And so now here, this is just going to be 0. But now here, when I take the derivative, the derivative of sine is cosine. I'll have x squared. So again, it's just like before, where I replace the t with whatever that upper limit is. However, when you differentiate this, because we have this set of parentheses here, that's usually a big clue that we're going to need a chain rule. So I need to multiply this by the derivative of the inside, so it'll be times 2x. So that's the one extra thing. So if I want to do this slightly differently, or different problem, if I want to do d dx derivative of, again, we'll say 2, I'll say 3x squared of, we'll say, tangent of t dt. What I do is I'm going to just replace t with that 3x squared, so tangent of 3x squared, but then I'm going to multiply by the derivative of that. I'm going to need a chain rule for that, and so that's going to be times 6x, and that's it. Final answer. So I appreciate you watching. Hope this helped. Thanks. Have a great day. See you in the next one.